Welcome to this discussion on a fascinating paper detailing SynFlowNet, a novel approach to generating diverse and novel molecules while explicitly considering synthesis constraints. This is a significant advancement in computer-aided drug design. Let's start with the core problem this research addresses. What are the limitations of existing generative models in drug discovery?
Current generative models in drug discovery often excel at capturing molecular motif distributions, but frequently produce molecules that are practically impossible to synthesize. This disconnect between in silico generation and real-world synthesis capabilities significantly hinders their application in drug development pipelines. Many methods operate on smile strings or assemble molecules from atoms or fragments, offering no guarantee of synthesizability. While synthetic accessibility scores exist, they are often oversimplified heuristics. Even computer-aided synthesis planning, while principled, is computationally expensive, making its integration into the generation process challenging.
So SynFlowNet aims to bridge this gap. How does its approach differ from existing methods? What is the fundamental innovation?
SynFlowNet leverages GFlowNets, a framework that generates diverse samples efficiently. Crucially, SynFlowNet's action space is defined by documented chemical reactions and purchasable reactants. This directly incorporates forward synthesis as an explicit constraint within the generative mechanism. The model doesn't just generate molecules, it generates plausible synthesis pathways.
The use of GFlowNets is key. Can you elaborate on why GFlowNets are particularly well suited for this task compared to other generative models or reinforcement learning RL approaches?
GFlowNets offer several advantages. They generate diverse samples proportionally to their reward, unlike RL, which often focuses on a single high-reward sequence. This diversity is crucial in drug discovery, where exploring different chemical spaces is essential. Furthermore, GFlowNets require fewer reward function evaluations than alternatives like MCMC or PPO, making them more computationally efficient for this complex problem.
The paper mentions challenges in representing the action space, particularly when scaling to a large number of building blocks, up to 200K. How did the authors address this scalability issue?
The authors cleverly address this by representing building blocks using Morgan fingerprints. Instead of a large learnable weight matrix for each building block, they use the fingerprint as a fixed representation. The probability of sampling a particular building block is then computed from the normalized dot product between its fingerprint and the current state's embedding vector. This significantly improves efficiency and scalability.
The paper also highlights a significant challenge inherent in using a reaction-based Markov decision process, MDP. With GFlowNets, the lack of guarantee that backward constructed trajectories will return to the initial state. Zero, how did the authors tackle this problem?
This is a crucial point. In a fragment-based MDP, removing nodes sequentially always leads back to S0. However, in a reaction-based MDP, a backward action might lead to a state that's not decomposable into building blocks, breaking the MDP. To address this, the authors explored several strategies for training the backward policy, VBE, including maximum likelihood estimation and a reinforce-based approach. These methods aim to ensure that EB avoids paths that don't terminate in S0, maintaining the integrity of the MDP. This is a novel contribution, addressing a previously underexplored aspect of GFlowNet design.
The results section shows SynFlowNet outperforming baselines in several key aspects. Can you summarize the key findings regarding synthesizability, diversity, and novelty?
SynFlowNet significantly improved synthesizability compared to fragment-based GFlowNets, achieving higher synthetic accessibility scores and retrosynthesis success rates. It also demonstrated superior diversity compared to RL methods, exploring multiple high-reward modes in the chemical space. Furthermore, SynFlowNet generated more novel molecules compared to other methods, showing a lower similarity to known drug-like molecules in Schimble.
The paper also explores the impact of training the backward policy. What were the key findings from this investigation?
Training the backward policy proved crucial for MDP consistency. Both the maximum likelihood and reinforced methods effectively prevented the backward policy from assigning flow to invalid paths, leading to improved sample quality and diversity. The reinforce approach, in particular, showed promise in balancing exploration and exploitation during backward trajectory generation.
The scalability experiments are also noteworthy. How did SynFlowNet perform when scaled to the entire enamine building block set, 221,181 molecules?
The fingerprint-based approach enabled SynFlowNet to scale effectively to the large enamine set. While increasing the number of building blocks generally reduced reward, the fingerprint method mitigated this effect significantly. Moreover, it allowed the model to utilize a much broader range of building blocks compared to the baseline approach, leading to greater diversity in the generated molecules.
Finally, the paper demonstrates the adaptability of SynFlowNet by incorporating experimental fragment screens. How did this integration improve the model's performance?
By curating the building block set based on experimentally validated fragments for a specific target, for OGM Pro, SynFlowNet's efficiency and performance were enhanced. This targeted approach led to a higher proportion of high-reward molecules, demonstrating the potential for integrating SynFlowNet with real-world drug discovery workflows.
This discussion has highlighted the significant contributions of this research. The development of SynFlowNet represents a substantial step forward in computer-aided drug design, addressing the critical challenge of synthesizability while maintaining diversity and novelty. The innovative use of GFlowNets, the clever handling of scalability issues, and the novel approach to training the backward policy are all noteworthy contributions. The integration with experimental data further enhances its practical applicability. Thank you for this insightful discussion.